record. Okay, so we're going to fill in all of the ratios. So you can do that on your own as I'm also filling in. So like sine of alpha, I look at alpha, that's opposite over hypotenuse. That would be the ratio A over C. So you're going through and writing down what each of these ratios are, okay? So then cosine of alpha would be adjacent over hypotenuse. Secant of alpha would be the reciprocal. Cosecant of alpha would be the reciprocal of sine. And I'm going to stop blah blahing for a sec. Okay. So after you have filled in all of your ratios, I want you to take note which of the ratios are the same. Like, hey, we have an A over C right here and an A over C over here. That means that sine of alpha is equal to cosine of beta, and I'll write that down after to summarize. We have a B over C and a B over C. C over B, C over B. C over A, C over A. A over B, A over B. And what color could I use that would be different? B over A, B over A. So looking at what I highlighted, I can see that sine of alpha is equal to cosine of beta. And we can also say that cosine of alpha is equal to sine of beta. And then we can say that secant of alpha is equal to cosecant of beta. And cosecant of alpha is equal to secant of beta. And that tangent of alpha is equal to cotangent of beta. And cotangent of alpha is equal to tangent of beta. Okay, next.
Can you just wait 1 second to write that down? Sorry.
Oh, of course, yes. Adam, I don't know if you remember when you asked me about the naming of the trig functions, like when we first started studying trig, and I sent you this document, I think to explain, or a picture of this page to explain. But it's every year when we start trig, everyone always goes, oh, well, the reciprocal of sine should be secant because it starts with S, and the reciprocal of cosine should be cosecant. But that's not the case, obviously. But the naming of the trig functions has nothing to do with reciprocals. It actually has to do with cofunctions, right? Cosine is the cofunction of sine. Cosecant is the cofunction of secant. Cotangent is the cofunction of tangent. Which leads me to the cofunction theorem. So a trigonometric function of an angle is always equal to the cofunction of the complement angle. And if you think back to geometry, complementary angles are two angles that sum to 90 degrees, or in radians, that would be pi over 2. So if we took that relationship, that complementary relationship, alpha plus beta equals to pi over 2, and we solved for beta, we would get beta equals to pi over 2 minus alpha. And then we think about replacing each of the betas here, with pi over 2 minus alpha. Well, that gives us our cofunction identities, right? That sine of alpha equals to cosine of pi over 2 minus alpha. Cosine of alpha then equals to sine of pi over 2 minus alpha. So the pi over 2 minus alpha just represents the complementary angle to the angle alpha. So for example, sine of 45 degrees, or pi over 4, is equal to cosine of pi over 4, right? 45 degrees and 45 degrees, or pi over 4 and pi over 4, well, those are two complementary angles to each other. They sum to 90 degrees. Cosine of 30 degrees is equal to sine of 60 degrees, right? Complementary angles, their cofunctions are equal to each other. So these are the cofunction identities. I'm showing them, part of the reason I do it here instead of 6.1 like they talk about in your textbook is they don't really use these identities in 6.1, right? 6.1, we were mostly practicing verifying identities, which there are some like that you could technically use. Times you could maybe use the cofunction identities to help you with verifying identities. But we're actually going to use the cofunction identities in our next set of derivations. They're often used in derivations. But I mean, we might in 6.2, I can't remember exactly, we might use them for some verifying. But remember, the point of the trig identities, at least for next year and us going forward in this class, will be for different derivations, but also rewriting complicated trig statements or functions in simpler forms. And sometimes cofunction identities need to be used. So you're going to need to memorize these guys. Put all caps. And it looks like a lot, but like, it's not. Like, it helps you, right? Sine and cosine. Secant, cosecant. Tangent, cotangent. Before I move on, does anyone have any questions? Okie dokie. Let's keep it going. So we're going to derive our sum and difference identities next. And you'll notice there are cosine sum and difference identities. That's on our first page that we're going to derive. There are sine sum and difference identities. And there are tangent sum and difference identities. I put angle in parentheses here because I think of it more as the angle sum and difference identities, and you'll see why. So once we derive the first one, which I believe will be the cosine difference identity. Yes, the cosine difference identity. I'll show you why I think of it as the angle difference identity. The cosine angle difference identity. The first derivation is complicated. This is the one that like, I'm not going to expect you to like recall on a test or anything. And I also don't think it's necessarily helpful for you to be able to derive this one because it's pretty complicated. But if you have this one, deriving the other ones is pretty straightforward. So first off, I want to make sure you guys understand this first picture on the left here. And this is a unit circle, which means that like this point right here would be 1, 0. But what this picture is an angle in quadrant 1, an angle that terminates in quadrant 1. So that would be the angle beta. And the point on the unit circle that corresponds to the angle beta would be cosine beta, sine beta. There's also an angle in quadrant 2 that I have named alpha. And the point on the unit circle that corresponds to that angle is cosine alpha, sine alpha, right? Because we are in the unit circle. The circle centered at the origin that has a radius of 1. There is an angle between the terminating side of beta and the terminating side of the angle alpha. And that angle could be calculated from taking angle alpha and subtracting angle beta. And I've just named, I wasn't creative for good reason here, and I just named that angle alpha minus beta. That's the angle name. The angle that you would get from taking the angle in quadrant 2 and subtracting the angle in quadrant 1. Does anyone have any questions about that picture? Okay. Now what the picture next to it is if we were to think about picking that angle up, the angle alpha minus beta, and rotating it and placing it into standard position. So standard position is, remember, whenever the angle starts on the positive x-axis and then terminates from either rotating in the counterclockwise direction or the clockwise direction. Counterclockwise is a positive angle, clockwise is a negative angle. So going from that first, out of the way. Oh no. Okay. So going from that first picture to that second picture, you're thinking about picking up the angle alpha minus beta, rotating it and placing it into standard position. My picture is probably not perfect, but that's supposed to be the same angle. We are in the unit circle still. So this point here is 1, 0. And then the point that corresponds to the angle alpha minus beta on the unit circle would be cosine of alpha minus beta, sine of alpha minus beta. Are there any questions of how I got from the first picture to this picture to the second picture? Does that make sense to everyone? Now,
wait, can you explain how you got that point, like, and like derive that? I'm a little confused.
This point right here?
Yes. Yeah.
Yes. Okay. So it's just the angle, right? Like the point over here, if this is the angle beta, then this point on the unit circle would be cosine beta, sine beta, right? And this is angle alpha, which is in standard position, starts on positive x-axis and rotates and terminates in quadrant 2. Then this point right here is cosine alpha comma sine alpha. So if we've taken the angle that was equal to alpha minus beta and put it into standard position, that means that this point right here would be cosine of the angle alpha minus beta, comma sine of the angle alpha minus beta. Like if alpha minus beta was equal to 60 degrees, that point would be cosine of 60 degrees, comma sine of 60 degrees. Alpha minus beta is just the angle name. Did that help?
Yeah, thank you.
Okay, good. Good. Weird angle name, I get it, but it's like the literal description of how we came up with that angle, taking the angle from quadrant 2 and subtracting the angle from quadrant 1. Now, I drew a green line between the points in this first picture. And I could call the distance between those points d sub 1. I'm going to name the distance between 1 comma 0 and cosine of alpha minus beta comma sine of alpha minus beta. I'm going to call that d sub 2, distance 2. You guys know, kind of proof by picture and logic, right? Like those two distances are equal to each other, right? Because we took the angle alpha minus beta and just and put it into standard position. Those two distances have to be equal. Okay, so leaving that picture for just a second, I want to remind you, although I know you all know this, of distance formula. Sure, everyone still remembers distance formula. Right, distance formula, or distance between 2 points in the XY plane, is the change in the X coordinates squared plus the change in the Y coordinates squared. So d sub 1, using distance formula, would be equal, in referencing the picture, to cosine beta minus cosine alpha squared plus sine beta minus sine alpha squared. D sub 2 would be equal to 1 minus cosine of alpha minus beta squared plus 0 minus sine of alpha minus beta squared. And since d sub 1 equals to d sub 2, that means this guy is equal to this guy. Okay, so before I continue, I want to check in with you guys. What are we okay with how we just got to where we are?
Can you explain the 0 and 1 part again?
Sure. Because looking at the second picture, right?
Because is it because we moved it to like the general position?
Yeah, to standard position, right? So
Okay.
this point right here becomes 1, 0. And then we have this point right here.
Oh, and that becomes the initial point. Okay, yeah. I think I got it.
So 1 minus, so change in x becomes 1 minus cosine of alpha minus beta. Change in y becomes 0 minus sine of alpha minus beta.
Yeah, I got it. Thank you.
Cool. Okay. So the left-hand side equals to the right-hand side of this really complicated, yucky looking thing. And we're going to make it a little more complicated, sort of. Yeah, kind of. So we're going to square each side of the equation, which would just get rid of the square roots, basically. So we would have cosine of beta minus cosine alpha squared plus sine beta minus sine alpha squared. 1 minus cosine alpha minus beta squared. And then because that's 0 minus sine of alpha minus beta squared, I can actually just simplify that to be plus sine squared of alpha minus beta.
But isn't it negative sign?
Right, but what happens if you square a negative?
Oh, duh.
Okay. We're going to make it look even more complicated right now, but it's really like it's not hard. It's going to look more complicated, but wasn't really complicated to get here. We're basically just going to multiply everything out. All the binomials that are squared, we're going to multiply all these bad boys out. And remember, that's not like that first cosine beta minus cosine alpha, all squared. That's not cosine squared beta minus cosine squared alpha. If you guys do something like that on a test, I'll give you a big fat 0. That is cosine beta minus cosine alpha times cosine beta minus cosine alpha. So you have to think about distributive property. So it ends up being cosine squared beta minus 2 cosine alpha cosine beta plus cosine squared alpha. That's for multiplying out that first binomial. Now we have to multiply out sine of beta minus sine alpha. So plus sine squared beta minus 2 sine alpha sine beta plus sine squared alpha. Whew, that's the left side. Okay, right-hand side, multiplying 1 minus cosine of alpha minus beta out. That's going to be 1 minus 2 cosine of alpha minus beta plus cosine squared of alpha minus beta. And then we still have the plus sine squared of alpha minus beta. That looks real complicated, doesn't it? Vincent Chen, do you have a comment or an idea?
Oh.
Can you make everything like 1?
Yeah,
and like
the
make them
cosine
all
squared
like
plus
1.
sine squared.
And then they're all like, it's like
that is all gonna cancel out. Oh my gosh, it's crazy.
It's like
I
3.
think you guys are on the right track. I think what you're saying is like, hey, there's a cosine squared beta and a sine squared beta on the left-hand side there. Well, cosine squared beta plus sine squared beta is going to be
1. Oh,
1.
1.
And then cosine squared alpha plus sine squared alpha is also going to be
1. And
God,
cosine
guys.
squared alpha minus beta and sine squared alpha minus beta.
It's going to be
1.
1. Right? So they're saying that's going to also simplify to 1. So after we have applied the Pythagorean identities, the left-hand side will end up simplifying to be 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta, and then 2 minus 2 cosine alpha minus beta. And if we thought about subtracting 2, so I think you guys also mentioned this, if we thought about subtracting 2 from each side, boom, boom, those 2's go away. And then we could also think about factoring out a -2 from the left side.
Couldn't you just divide everything by -2 on both sides?
Yeah, you could. You could do that. I'm just trying to make sure that everyone is able to see that. But yeah, if you want to skip to that step, that's fine. Right? Because then if we were, like Emmett said, if we were to divide by -2 on each side, boom, boom, those go away. And then, oh my gosh, that is our first identity. So it's the cosine difference identity, which I'm going to flip around because we usually have it memorized as cosine alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. And you guys, there's going to be 6 sum and difference identities, and I have a little rhyme to help you memorize them once we finish deriving them all. These guys are, these sum and difference identities are going to be very handy though. Now, that's the difference identity for cosine. There is a sum identity for cosine, which can easily be derived by the fact, oops, darn it, that cosine of alpha plus beta, right? We're trying to derive that identity, the sum identity, which do you guys see why I call it the angle difference identity and angle sum identity, right? Alpha minus beta, alpha plus beta. Cosine of alpha plus beta can also be thought of as cosine of alpha minus negative beta. Where if we think about applying the identity that we just derived, but replacing all of the betas with negative beta, we would have cosine alpha, cosine negative beta, plus sine alpha, sine negative beta. And then applying the even odd identities, right? Cosine of negative beta is actually just cosine of beta. Sine of negative beta would be negative sine of beta. So oops, we can rewrite that as minus sine alpha sine beta. So that's the sum identity for cosine. Cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta.
Wait, can you wait 1 second?
Of course.
We don't have to like know how to do the deriving, right?
No, it can be helpful, like the angle sum and difference identities. I mean, it could be helpful understanding the derivations, but they're kind of the big ones that would be challenging to derive. But like you'll see that once we know the angle sum and difference identities, then deriving like the double angle identities is going to be a piece of cake if we know these. So like if you were to, for some reason, forget what the double angle identities are, but you remember the sum identities, then you can, boom, just derive the double angle identity. But that's what I meant is like, especially the difference identity for cosine, like that's too complicated to try and derive like on the spot. But this is also the honors class, and I think a lot of you guys, when I give you different formulas, like when we talk about different formulas and stuff, you're curious about where did they come from? You guys, are we caught up? Is it okay to move on?
Yeah.
So you guys, next we're going to do the sine, sum, and difference identities. And these ones are pretty simple.
I don't know if I believe you.
Well, they're not, compared to what we just did, that was the hardest part. Okay, so if you remember the cofunction identity, right? Sine of alpha equals cosine of pi over 2 minus alpha. Well, that would mean if we have sine of alpha plus beta, that's equal to cosine of pi over 2 minus alpha plus beta. Just applying the cofunction identity right there. Do we see that, you guys?
I'm confused about how you did that.
Same.
Does that help? Right?
Oh, yeah.
Alpha plus beta is the angle. I realize it's confusing because you're like, wait, alpha and beta are two different angles. But alpha, if you're evaluating sine at alpha plus beta represents one angle. So the angle that's complementary to the angle alpha plus beta would be pi over 2 minus alpha plus beta. Did that help?
Sorta, yeah.
Okay. So,
Wait, Mr. Set,
yes.
will that always work? Because it's like, because you said something about having to be like in the first quadrant. Like, how would you know that you can use it then?
Well, it could be a negative angle, right?
So you
It
can you
doesn't-
always use this or?
Yes.
Okay.
Right? If we, yes. Because whatever this angle represents would be the angle that's complementary that would sum with pi alpha plus beta to be equal to pi over 2. So we used quadrant 1 and quadrant 2 for the picture for simplicity, but it doesn't necessarily have to be quadrant 1 or quadrant 2 for those angles. But really good question. Okay, so the next thing we're going to do is I'm going to think about distributing this negative so that I would have cosine of pi over 2 minus alpha minus beta. And then by the associative property of addition, I'm allowed to regroup the pi over 2 minus alpha. Remember all those different like properties of real numbers that you learned back in algebra 1 and you're like, why do I have to learn these names of these different properties? Well, because we often have to apply those properties. Okay, so from there, I want you to think about pi over 2 minus alpha as one angle and beta as a second angle. Because then we're going to apply the difference identity for cosine, right? This identity up here. So we would have cosine of pi over 2 minus alpha times cosine of beta plus sine of pi over 2 minus alpha times sine of beta.
Wait, so can you like explain like just really quickly how you went from the second step to the third step? I'm still a little confused about that.
Okay, so thinking, let me see if I can help with like a visual. So what if you thought of this as, no, I use alphas and beta. Like what if you
Beta.
thought of that as like angle X and that is angle Y? And if we go up here, and like if you thought of this as cosine of X minus Y, right? Cosine X times cosine Y plus sine X times sine Y. So thinking of these as a difference of two angles so that I could apply the difference identity for cosine. Did I make it more confusing throwing X's and Y's in there?
A little bit, it's okay.
Let's see.
Yeah, I'm still a bit confused as well.
Okay. Oops.
Is it mostly going from the multiplication to the addition, or?
One sec. Ah! Okay.
Wait, so on the left side, the cosine of alpha minus beta and the sine of alpha plus beta, those are the same then, right?
Say that one more time.
Like, because you're plugging in the right part of the cosine sum, one of the cosine sum and difference identities. Like the left part of it's like cosine of alpha minus beta. Is that the same as sine of alpha plus beta from like down there?
What I'm comparing is that cosine of alpha minus beta is like cosine of pi over 2 minus alpha minus beta.
Oh, I see. Never mind.
And then applying the right-hand side of the difference identity, you get this.
And then can you just swap the cosine pi over 2 minus that blank and that for the other thing.
Using cofunction. Yep.
Yeah.
For the cofunction. Yep.
Ooh.
Okay, so Adam, Audrey, I want to hear from you guys. Did that help at all with understanding how I got from that second to third line?
Like, kind of. I'm gonna have to rewatch the video though later to
I'm
like.
gonna rewatch it anyway. Yeah.
Okay. Maybe you'll have like a moment where you're like, oh, I get it in a minute. These are hard, you guys. These are complicated. I get it. It's hard to see. So what we're going to do next is what Vincent was just mentioning, that we're going to replace the cosine of pi over 2 minus alpha with its identity, which is just sine alpha. And then we're going to replace the sine of pi over 2 minus alpha with its cofunction identity, which is just cosine alpha. So that's the sum identity for sine. I'm going to write it out again.
So if you're going back to that, then why did you use pi over 2 in the first place again? Just to like get there, kind of?
So we could use the cosine difference.
Yeah, so that we could use the cosine difference identity to help us get the sine sum identity. Right? Because all we have at this point, we're trying to find what the sum identity is for sine, and all we really have are those other identities that we've talked about, but also the cosine sum and difference identities. So we're able to go back and apply the cosine difference identity, so this one up here, by rewriting sine of alpha plus beta using that cofunction identity. Just let it kind of like marinate. This isn't something I'm going to test you on, you guys. It is cool to be able to see it and to like understand like, oh my gosh, we got from here to here to here, and like see where it came from, but like don't let it stress you out too much.
Can you hold it there for 1 second so I can just?
Yeah. And then the difference identity for sine, we're going to find in a similar way that we found the sum identity for cosine. So by rewriting, and I already have it there, so by rewriting alpha minus beta as alpha plus negative beta, so that you can apply, maybe you can try this on your own if you're waiting for me, you can just apply the identity that we just derived. Add water.
Oh, you can go on. I got it.
Oh, okay, thank you. Okay, so from here, just referencing the identity that we just derived, we'll have sine of alpha cosine of negative beta plus cosine alpha times sine of negative beta. And then thinking even odd identities to simplify. Okay, so sine alpha
Could you zoom in a bit to like,
I like zoomed out. Okay.
thank you.
And then I'll show you the condensed version of these 4 identities next time so that the chant makes sense. Sine, cosine, cosine, sine, cosine, cosine, sine, sine. I got that from Mr. Almernon. It's very sad I don't have him next door anymore to like help me out with that stuff. But you guys, this is,
1 more second, sorry.
oh no, you're fine. We're gonna stop here for today. If any of you wanted to look, no, the tangent sum identity is kind of complicated because you have to multiply by a weird version of 1. But we'll pick up with the tangent sum and difference identities next time. So you guys, well, next time we'll like I just said, we'll pick up with the tangent sum and difference identities, double angle identities. Ooh, angle spelled wrong there. Is very simple to derive from the angle sum and difference identities, angle sum identities specifically. Power reducing identities can be derived from double angle identities. Half angle identities can be derived from the power reducing identity. So I have these in order, but we did the most intense derivation today. So you should give yourself a pat on the back for sitting through that. I'm going to stop recording.